So our first speaker is Georgios Moschidis. He's a Miller Fellow at UC Berkeley, and he's going to be speaking to us about instability of ADS.
Thank you, Jordan, for the introduction. And thanks a lot for the invitation. It's a great honor for me to speak here at the Black Hole Initiative. Now, as the title suggests, I will be talking about the instability of under de Sitter spacetime. So I will be talking about the case of negative cosmological constant. And let me start by introducing the main object of this talk, namely under de Sitter spacetime. So in general, okay, let me mention already that in this talk I will only focus in the case of 3+1 dimensions. Of course, everything that I will say can be generalized in higher dimensions, but not in 2+1 dimensions. Okay? So, in 3+1 dimensions, the under de Sitter metric looks like that. This is the simplest solution of the vacuum Einstein equations with a negative cosmological constant. And under de Sitter spacetime has a very curious geometric property. So it can be conformally identified with the interior of a cylinder, in fact with the interior of the northern hemisphere cross R. And in this way one sees that through this conformal identification, under de Sitter spacetime has a conformal boundary at infinity, this time-like surface here, which corresponds to R equals infinity, let's say in these coordinates. And the existence of this conformal time-like boundary at infinity means that, for example, every null geodesic in this spacetime has ideal endpoints, future endpoints and past endpoints on this boundary at infinity. And this has the consequence that if we want to study on under de Sitter spacetime some hyperbolic equation, let's say the scalar wave equation, we really have to specify boundary conditions at infinity that will tell us how information that flows from the boundary into the spacetime behaves, right? So more generally in this talk, we will talk about asymptotically under de Sitter spacetime. So these are spacetimes that have a similar time-like conformal boundary at infinity, but the interior of the metric here could differ a lot from the under de Sitter metric that I wrote down. And of course, these spacetimes are ubiquitous in the context of the ADS-CFT correspondence. Okay, so of course we'll be interested in the dynamics of asymptotically under de Sitter spacetime. So we want to see how such spacetimes evolve in time, given some initial data. And this question, of course, makes sense because the Einstein vacuum equations are of hyperbolic nature. So in order to study such questions regarding dynamics, traditionally one would write down an initial value problem. So given initial data, the question would be how does the development for the equation looks like. But remember, because of the boundary at infinity, we also have to specify boundary conditions. So the framework that we will work in is that of the initial boundary value problem. So let me switch back here. So what we'll do is that we will prescribe initial data on a hypersurface like that, and boundary conditions at infinity, and study the evolution of the spacetime according, let's say, to the vacuum equations, or to the equations with matter. So for the vacuum equations, the initial data will of course consist of a three-dimensional space-like hypersurface, equipped with the induced Riemannian metric and the second fundamental form. And the boundary conditions, again for the vacuum equation, this will correspond to fixing the conformal structure of the time-like boundary at infinity. And of course, okay, the fact that this combination of initial data and boundary conditions give rise to a well-posed initial boundary value problem, this is highly non-trivial. And the person who first solved the existence of solutions for any such given combination of data was Helmut Friedrich in 1995. Of course, if one adds matter to the equations, one should also specify initial data and boundary conditions for the matter fields, and this makes the problem even more interesting. But let me just mention that, okay, within this large class of boundary conditions at infinity, of course there is a smaller class of conditions which are dissipative. These are conditions for which the energy flux on the boundary in the outward direction is non-negative. And within this class, there is a unique reflecting boundary condition. This reflecting boundary condition is the one for which the energy flux at the boundary is zero. And this is exactly the condition that the conformal metric induced on the boundary lies in the same conformal class as that of the round sphere cross R. Maybe rescaled according to a factor depending on the cosmological constant.
Sorry,
yes.
I don't understand what you're saying. Isn't the black hole formation a counterexample? So you're saying it exists under some circumstances.
This statement here is that given some initial data, for some time there exists a
existence of solutions for some finite time.
For some finite time, of course. And this means that there exists some maximal development. Now, within the maximal development,
I'm sorry, I didn't understand what you meant. I thought you were talking about
singularities could even create after some longer time. Yeah. Okay, but given this, if you want, fundamental theorem, this is just a theorem that says, given initial data and boundary conditions, local in time some solution exists and is unique in some sense, but it didn't specify. So given such statement, one now is in a position to ask questions about the dynamics, namely questions like, given some class of initial data and boundary conditions, what are the properties of the maximal development corresponding to those? Is there a trapped surface? Is there a black hole or some singularity? And let me start with the most trivial question about dynamics that one can ask, which is the question of stability of the trivial solution. So the trivial solution in this case is under de Sitter spacetime, and the question one can ask is what happens if we perturb the initial data of under de Sitter spacetime ever so slightly. So the conjecture proposed by Dafermos and Holziger in 2006 was the following: that if one fixes reflecting boundary conditions at infinity, remember there is a unique reflecting boundary condition in this class, then there exists a family of arbitrarily small perturbations of the initial data of under de Sitter spacetime, such that if one waits for long enough time, this perturbation will create a black hole region. Right? And because there is no black hole region present in under de Sitter spacetime, this really is an instability statement. Because once a black hole region forms, we're already very far away from under de Sitter spacetime. Okay.
So that conjecture must have come with a definition of what small is, because it would be true
Exactly.
even for
This
flat
is
space.
the right question. So somehow, how should smallness be understood here? Of course, smallness of course should be understood in terms of some norm measuring the size of the initial data. So we have to specify how we measure the size of the initial data. The minimal requirement for such a norm would be a norm where, let's say, well-Posedness holds. Right? So, for example, one could assume, let's say, a right statement for smallness would be if, let's say, the initial data and, let's say, 10 derivatives of those initial data are small in some weighted norm towards the boundary. Let's say, a quantity that is not right to measure smallness is the total ADM mass of infinity. So the statement that the total ADM mass is small is not enough, because you can have initial data with arbitrarily small ADM mass, which in arbitrarily small time create a black hole. Right? So it is understood here that the statement of smallness is in some context where well-Posedness holds, and for which, the statement will be that for any given time, if the initial data are small enough, in this given time interval, the solution will almost look like ADS. Nothing bad can happen for fixed times. We have to wait for very, very long times to see. But of course, let me mention that this conjecture also applies to not just for the vacuum case. It's also a valid conjecture in the case of reasonable matter models. Reasonable in the sense that, in terms of, let's say, stability properties of the matter model itself. And let me also mention that it's crucial for this conjecture that the boundary conditions chosen are reflecting ones. Because if one allows for some dissipation, in fact, if one allows for maximal dissipation, if one chooses optimal dissipative boundary conditions, then by the work of Holziger, Luke, Smolevich, and Warning, unsurprisingly, one sees that actually under de Sitter spacetime is asymptotically stable under such perturbation because of the strong dissipation of the boundary.
Is there a reason, so in making this conjecture, there's some underlying intuition that it should be so?
So
what is that based on?
When this conjecture was made, the intuition was, if you want, maybe a bit naive, in the sense that the intuition was that you have some perturbations, because of the reflecting condition, this perturbation cannot escape space-time.
Mm-hmm.
Now you have some nonlinear equation governing this perturbation, so you have nonlinear self-interactions, which can lead to nasty things happening.
Mm-hmm.
But at that point, that was the level of the argument. However, since then, a lot of work has been done on this. Of course, most work, if one wanted to prove this conjecture, of course, it suffices to construct a family of unstable initial data. And in order to construct a family, the easiest, let's say, the obvious approach would be to assume some symmetry in order to make our life easier. And ideally, we would like to reduce the problem to a 1 + 1 dimensional hyperbolic system. So let's assume spherical symmetry. This is consistent with ADS asymptotic. Of course, in spherical symmetry, the vacuum equations are trivial. So let's look at the Einstein scalar field system instead. And so the first groundbreaking work in this direction was by Bizon and Rostvorovsky, who did both a numerical and a heuristic analysis of the problem. So numerically, they verified the conjecture, at least, let's say, for this system, but they also they were the first to propose a heuristic mechanism for the instability. And the mechanism that they suggested was the following. So we're looking at the Einstein scalar field system, so let's look at the initial data for the scalar field, and let's decompose the scalar field into modes. Right? So if we're looking at the linear wave equation, these modes would evolve independently of each other. But now, once we turn on the nonlinear interactions, the modes will exchange energy with each other. And in this Swarovski, they noticed that with Dirichlet boundary conditions at infinity for the scalar field, what happens is that there are a lot of resonant interactions in this, let's say, system of interacting modes. And these resonant interactions lead to energy flowing from low frequency modes to high frequency modes. So they suggested that, and remember, at the end of the day, we want to solve trapped surface formation, black hole gluon formation. And the black hole forms, in order for a black hole to form, enough energy has to be concentrated at small scales.
Mhm.
So this mechanism of energy flowing to smaller and smaller scales was the first heuristic mechanism, of course.
Mhm.
And since then, a lot of numerical heuristic works have been found. So,
I thought, could one also understand it this way? It's like a box, and the stuff rattles around in the box, and it never disperses out to infinity.
exactly. So,
So if you
they
wait
reflect-
long enough, randomly move around, if you wait long enough, it will happen to be concentrated within a Schwarzschild radius, and then you get a
But
black
that's-
hole.
But so this really depends on the equation. That's true. But let's say there are some special equations. Let's say there are examples of completely integrable equations for which this will never happen.
Right,
But let's
it's
say-
integrable that way.
Yes, exactly. So the question is, so let's say, and the question that say this was wanted to address was somehow not just the question of whether just an unstable family exists, but the question of how generic this picture is at the, let's say, within the class of initial data. Somehow, is it true that for a generic perturbation this will happen, or can it be the case that islands of stability exist, in the sense that are there some perturbations which somehow give rise to some quasi-periodic solutions, which are, let's say, these special solutions could be stable under perturbations. So these type of questions are the ones that somehow people have studied, both numerically and heuristically. But let me mention that, let's say, using this approach, the approach of resonant mode interactions, there has not been a rigorous proof so far of the conjecture. So what I want to do now is I want to present to you a rigorous proof of the conjecture, at least sketch the main idea of that. And in order to do that, what I will do is that I will introduce an alternative approach, an alternative, if you want, mechanism of instability. And in some sense, this you can feel that this is necessary if one wants to go all the way up to the level of trapped surface formation, because the resonant mixing mechanism is valid only as long as the perturbative analysis holds. So as long as you can really assume that your background is close to ATS, so that the notion of a mode solution somehow makes sense. So what I'm going to do now, so what I have been doing in the past few years, is that I will introduce a mechanism which studies, let's say, which is based on the interaction of wave packets in physical space and makes use of the monotonicity properties of the equation. So this will really depend on the structure of the Einstein equations in a more fundamental way than the resonant interaction. Okay, so what I will do is that first I will sketch this mechanism on a, let's say,
Does
simple
monotonicity
model.
mean going towards smaller and smaller wavelengths?
So monotonicity, no, what I mean by monotonicity is, for example, if you look at part of the equations, let's say the Rexadur equations, some quantities really focus, can only focus. So I want to use this type of properties in connection, let's say, with the interaction of wave packets. And okay, let me make this more precise. Let me just sketch a simple example where the mechanism works, and then let me move to the statement of the result. So what we're going to do now, so remember, we want to prove that we start from some initial data, which are small initially, and then after a very long time, a trapped surface forms. So what I'm going to do is that I'm going to assume that the initial data are organized so that they give rise to a large number of narrow beams. Right? So we have a large number of narrow beams. These beams are initially ingoing. They move towards r equals 0. Then, of course, at some point, the beams will, if you have a spherical symmetric beam, it will go through r equals 0, at least you expect so, and then it will come out of it as an outgoing beam. So these beams will become outgoing afterwards. Then they will be reflected at infinity. We'll have assumed some reflecting boundary condition, and this thing will, let's say, the beams will keep this shape for a very long time. And as along this evolution, you see that these beams interact with each other. Now, let's make a few basic assumptions that we'll have to verify later in the proof. So the assumption is that because the beams are very narrow, at least away from r equals 0, we will assume that some geometrical optics approximation holds. In particular, these beams approximately solve the Einstein null dust system. Of course, close to r equals 0, this approximation will break down. And indeed, the very specific properties of the matter model used will have to be used to see what happens to the beam there. But remember, so far we're looking at spherical symmetric beams of matter, which interact with each other. And so let me just focus on the like two beams interacting with each other. Now, what I want to do is that I want to see how these beams exchange energy with each other, and the right way to measure the energy of a beam, at least in the spherically symmetric case, is just by looking at the difference of the Hawking mass, in fact the renormalized Hawking mass, in the region, in the outward region, in the inner region defined by the beam. And since we want to show that at some point a black hole region forms, or in other words, a trapped sphere appears, what we have to show in the end is that we want to show that there exists a point in the future where the 2m, 2 times the Hawking mass, divided by the radius of the sphere, becomes bigger than 1. So once we show that such a point appears, then this means that we're already in a black hole region. Okay, so by defining the energy of the beams in this way, and remember, because we assume the reflecting boundary conditions of infinity, whenever a beam reaches the boundary, its energy doesn't change. But the energy of the beam will change after each interaction with another one, because of nonlinear phenomena. Let me try to study how the energy of the beam changes when an interaction happens. So let me zoom in at two interacting beams, and let me assume that at the interaction here, the geometric optics approximation still holds. So this beam solves the Einstein null justice. So if this is true, then we can do a very simple calculation and see that whenever you have such a configuration, the energy of the ingoing beam increases while the energy of the outgoing beam decreases. This is where the monotonistic properties of the equations somehow appear for the first time. Because this is the only formula that I will write down in this talk. Okay. So you can actually do an estimate, a simple estimate for how large this energy exchange is. So what happens is that the energy of the ingoing beam increases by a factor which depends on the energy of the other beam, and this factor is bigger when r is small. So when this interaction takes place close to r equals 0. And of course the energy of the other beam decreases, of the outgoing beam has to decrease by a similar factor, because of course the total energy of the two beams has to be conserved.
What's that until then?
So here, this is just an equation for the renormalized Hawking mass in the Einstein null dust system. Yeah,
Are you using conservation of the Hawking mass or the actual energy?
So what happens? So I actually do the computation of the Hawking mass because, let's say, in these regions here, outside of the beam, the Hawking mass is constant because these regions are, I assume here that they are valuable.
Mm-hmm.
So what I want to do now is that and the difference, let's say, between the Hawking mass here and here gives me the energy of this beam. So I want to see how the difference of the Hawking mass here and here are related with each other. So what I want to do is that I really want to integrate the equation for the Hawking mass, over the region of interaction and see what I can get. So I don't want to tie with the, let's say.
So this argument sounds like this mass inflation that Poisson and company were.
Exactly.
It is the same phenomenon.
It's exactly. If you want this equation, appears there.
Okay,
Exactly.
fine.
Exactly.
The negative cosmological constant is changing it somehow?
So this is why I have here the renormalized Hawking mass, because the renormalized Hawking mass is the Hawking mass that is, let's say, is the quantity that is constant on Schwarzschild ADS. So it's the usual Hawking mass after we subtract from it a quantity which depends on the cosmological constant. So it's, if you want to be, let's say, if this is the Hawking mass, this is the renormalized Hawking mass. But
But for the mass crossing, negative lambda is not important.
Exactly.
Only for the reflection, right?
Exactly.
You want to do it
exactly,
again
exactly.
and again.
So when we're close to r equals 0, somehow the cosmological constant will not matter.
Will not
Exactly.
matter, right?
Exactly. Okay, so now that we saw this, let's just zoom out a little bit and let's follow the interaction of two beams for long times. So initially we have two beams. This is the exterior one, this is the interior one. At the first point of interaction, this one is ingoing, the other one is outgoing, which means that this one will gain energy from the interaction. Because remember, ingoing beams always gain energy in such interactions. Then these beams will interact again close to infinity, and now the beam that was ingoing before is now outgoing. So now it will lose some energy. But remember, the strength of the interaction, in these factors that I wrote down before, the interaction is stronger close to r equals 0 and weaker close to r equals infinity. Which means that this beam gains a lot of energy here and loses just a bit of energy here. So all in all, after one interaction, this beam has gained energy from the other one. And this can possibly continue for a long time. So we see that here we have a mechanism which leads to energy flowing, let's say, from beams which initially lie to the left towards beams which initially lie to the right. And if we could make sure that the beams which lie to the right are narrower than the beams on the left, this actually means that energy flows to smaller scales, to beams which are narrower. Right?
Excuse me, could
Yes.
it be any possibility that the outgoing beam lose so much energy that becomes
Exactly, so-
ingoing?
So actually, what can happen is that the beams can really decohere and not be beams anymore. But let me go back to this in a moment. So here I just want to sketch a heuristic mechanism, and now we'll talk about the details of let's say, rigorous implementation. But you're totally right, that's a main difficulty. But what I want to stress is that through this mechanism, through this non-linear interaction mechanism, we have devised a heuristic which can lead to energy flowing to smaller and smaller scales, provided we can arrange a matter model into such a configuration of beams. So let's now see how this heuristic mechanism can be rigorously implemented for a long time. And okay, let me mention that in order to implement this mechanism, we have to use matter models which allow for the arrangement of matter into localized, almost null beams. And this was first done by me a bit more than a year ago for the Einstein massless Vlasov system. In that case, I will not go into the details, but the massless Vlasov matter can be really localized into exactly localized matter beams. So you can have a configuration of exactly localized beams, and the spacetime will be exactly vacuum outside of them. However, this mechanism can also be applied to the case of the Einstein scalar field system. So this is the new result that I wanted to present here. And the statement of the result is what you would expect. So the statement is that in the case of the spherically symmetric Einstein scalar field system, there exist arbitrarily small perturbations to the ADS initial data. Now, arbitrarily small with respect to a certain scale invariant norm for which well-posedness holds. This is the bounded variation norm of crystal 2. You can write it down if you want later. And the statement is that there exist arbitrarily small initial data in these norms such that under evolution with either Dirichlet or Neumann boundary conditions at infinity, one gets a black hole region if one waits long enough. Long enough depending on how small the initial data were. Okay, so let me say a few things about how.
Well, you're not saying that every.
No, I'm not saying that every initial data, exactly. And
That
actually,
could
I can't.
be true, couldn't it?
It's
Or almost every.
so actually. So I cannot say anything even about the size of the region of the initial data which are, let's say, linked up to this probability. However, I can, if you want, I can comment about it later somehow. The mechanism is such that, let's say, if one wants to see what happens in the case of, the candidates for long-lived quasi-periodic solutions, somehow the picture actually is not so clear as one would expect, let's say, just from the time scale suggested by the resonant mode mixing. But let me comment on that. Okay, so what we want to do is that we want to try to implement the previous heuristics for the case of the Einstein scalar field system. So what we do is that we start with initial data which have the form of a large number of beams. So we start with initial data here, we have a very, very large number of beams, and each beam, as we move to the right, becomes narrower and narrower. So remember, narrower beams, this contains scalar fields which is concentrated in higher frequencies. The narrower the beam, the closer it will reach to R equals 0. Because the geometric optics approximation will be valid for longer times if the beam is very narrow. And what we do is that initially we spread the total energy of the scalar field into this large number of beams. But of course, because we're dealing with a scalar field, the beams will not remain localized. Actually, we will always have some decoherence of the beams. And the decoherence will become stronger whenever each beam reaches close to R equals 0. This is because these beams, they actually satisfy, so the equation satisfied, the scalar field equation, close to R equals 0, has a strongly nonlinear term, which comes from the interaction of the background, which is through the Hawking mass, which in turn depends on the scalar field phi, with itself. And actually, even if we make these beams narrower and narrower, decoherence will still be quite strong close to R equals 0. So we cannot get rid of decoherence by some symmetry. So this is something that we have to deal with. And okay, I'm not going to tell you the details, but somehow there is a trick that one can implement, and the trick is to study, let's say, a modified wave equation, but in choosing the modification so that the modified equation has stronger coherence properties, and the error term between the modified equation and the actual equation can be controlled in the scale invariant norm that I mentioned before. But let me go into details. Let me just mention that by using some technical machinery which was developed particularly for that, one can go all the way from, let's say, the small initial data up to the regime of trapped surface formation. But in order to achieve trapped surface formation, something very special must be arranged in the very last step. So what I did for that is the following. So I chose the initial data so that until the very last interaction before trapped surface formation holds, what happens is that in the part of the spacetime preceding this region, 2m over r is still very small. So we have a spacetime where 2m over r is small, but of course some other scaling variables of the solution have to become large, like we did, And what happens at the last interaction here is that all the beams that enter this region have an energy profile which decreases exponentially fast with the number of the beams. So the first, let's say the size of the first beam is like delta, the next one will be delta times e to the minus delta, and so on. And then what happens if we look at the precise formulas for the interaction is that after all these interactions, what will happen is that 2m over r, so this is the final beam, right? And the value of 2m over r along each intersection will be like a small constant. And now this means that if the number of beams is very large, if we look at the energy of the final beam, its energy will be, if you want, blue shifted by a very, very large factor. So what will happen is that the final beam will enter with an energy which is small compared to its size, and it will exit with an energy content which is very large compared to the size. And actually, by using an argument similar to the one used by Christodoulou, this will imply that a black hole, if you want a trapped surface, will appear along this beam before this beam reaches the closest point to r equals 0. This is inevitable because of this relation between the energy and the size of the beam. Of course, okay, let me sweep under the rug all the technical difficulties associated with this control. And let me just mention that, okay, this argument was an argument leading to a rigorous proof of the instability in the case of the spherically symmetric Einstein scalar field system. And in higher dimensions, let's say in 4+1 dimensions, where the vacuum equations can be reduced under the Bianchi 9 symmetry to a system which really looks like the Einstein scalar field system in spherical symmetry, the same techniques should be applicable. However, at the end of the day, I'm interested in the case of the vacuum equations, which in 3+1 dimensions cannot be reduced under symmetry to any 1+1 dimensional hyperbolic system. And the question is, can this heuristic mechanism be implemented to give a proof of instability in that case? And I believe that yes, this can be done. And there are two major technical obstacles to achieving this. The first one is actually to define, it's actually to give a well-Poisson's theorem in a topology of the initial data which allow for such type of perturbations to be considered small. And this can be done, this is work in progress, but this is. The second, if you want, important technical obstacle is what happens at the boundary. Because so far, in this discussion, I avoided saying anything about how these beams behave at the boundary. I just said that some reflection happened. And it is the case that in spherical symmetry, boundary effects are actually relatively easy to treat. But outside spherical symmetry, they pose a very serious technical hazard. But anyway, this is a roadmap I suggest for the proof of the conjecture in the vacuum case. I hope I'm not too over time. Thank you for that.
Questions for Georgios? Maybe just a quick one, but maybe we can talk about this after. But the dynamical formation of trapped surfaces at Christodoulou, as you know, of course, is to some extent about getting a tension, controlling the tension between the region of existence and the focusing mechanism. And the short pulse data is precisely designed to do this.
Exactly.
So having that in mind, how should I view the argument you just described to us? How do I understand this tension playing out in this setup?
So in this setup, somehow the whole, if you want, one of the main obstacles to show that up to the last set of interactions that I gave this picture here, if you want, in this tension between focusing and existence wins.
Okay.
And somehow the tension between them becomes comparable. The two effects can become comparable only at the very last step. So in order to achieve that, one really has to make sure that, let's say, at least the way I could see it, that somehow the final profile has this exponential configuration. So that at the time before this this last set of interactions somehow, yeah, this in this game somehow existence works.
So, I think right in the beginning you said you are going to discuss 3 plus 1, but it will work for 4 plus 1, 5 plus 1,
Yes.
anything larger, but not for 2 plus 1. Is that right?
Exactly.
So does this mean that this mass inflation phenomenon, again, does not work in 2D?
So the problem is the following somehow. In 2D,
Yeah.
of course, the total mass is conserved,
Yeah.
but the scale invariant quantity that measures, let's say, trapped surface formation is the mass. While in higher dimensions, let's say, in 3 dimensions, the quantity that measures if we're close to trapped surface formation was 2m over r.
Ah, right.
Exactly. So in 2 plus 1 dimensions, somehow there is no. So what happens is that. So let's say this mass inflation mechanism. What happens is that it makes the beams, if you want, more singular. So higher order derivatives
So
of
it
the
does
metric
narrow
will
it.
grow indefinitely.
Okay.
Exactly. But the total energy will be the same. So,
Okay.
so let's say for small initial data, no trapped surface will form, but higher order derivatives of the solution will grow. So there is some turbulence. But let's say-
Turbulence, there is power flowing to small scales.
Exactly.
Beams are getting narrow, but that's not enough to make a black hole.
Exactly. So
Basically,
of course,
that's the
something
point.
else could happen. I mean,
Yeah, yeah.
negative
Okay.
charge, so-
I think I understand. Yeah, thanks.
Yeah, okay, so let's thank Georgios for his talk.
Now our next speaker is Jason Dexter. Jason is visiting us from Colorado University in Boulder. He's an assistant professor there and a member of both Gravity and the HD, important contributor to the polarimetric study and theory studies of both collaborations.
And you have a brick wall between the two.
Something like
No leakage of signals.
no. Okay. Yeah, well, thanks a lot for the invitation. I was last here at the BHI a little over 2 years ago, and it's really a pleasure to be back. It's, first of all, great to see this place continue to thrive. It's really lovely. And the other thing is that in the field I work in, which is trying to image gas very close to black holes, a tremendous amount has changed since I was here last. So I'll talk a little bit about some of that I'm particularly excited about today. And of course, the reason that that's all changed is due to 2 large collaborations. The Event Horizon Telescope and this Gravity collaboration, 2 large international collaborations. And obviously a lot of people in the room have had a lot to do with this. I think the names and greens are students and postdocs that I've worked with on this. Okay, so now that we can resolve the near horizon regions of black holes and image them, what do we want to do? So for me, I'd say basically there's 2 things. And the first thing that I'm really excited about is learning basically how do black holes grow by accreting gas, and how do they power jets. We draw these, well, we see these real jets here in extragalactic sources, and have schematic pictures of gas falling onto black holes and driving jets like this cartoon. And these both rely critically on the role of magnetic fields in ionized plasmas. So magnetic fields are supposed to produce torques, which allow material to fall in onto the black hole through the event horizon, and they're also supposed to be able to extract spin energy of the black hole itself to power these jets that we observe. So the first thing is we would really like to know, test all that. Do magnetic fields really do these things? Can we find evidence of this when we look very close to the event horizon of black holes? Okay, so the first thing. The second thing is really with the nature of black holes themselves. We see in the center of our galaxy for a long time now monitoring stellar orbits. These are simulated data based on near-infrared observations of the center of the Milky Way, and especially this star here, shown here, has completed now almost two orbits over 25 years. It's gone through closest approach twice, and measures the mass and set its orbit to be 4 million times the mass of the sun. And you can see just sort of based on the number of these stars, you're not going to get that amount of material. There's not going to be 4 million stars inside there, and it must be a black hole. And we've also, as of 2018, measured for the first time the gravitational redshift effect. So you can start to measure relativistic effects with this work. Nonetheless, with the stellar orbits, the closest in star here, in the best case we know of in the center of our galaxy, just because it's very close to us, you're still at about 1,000 times the Schwarzschild radius. This is actually quite far away. So the idea is if you can go in much, much closer, what can you say about the nature of astrophysical black holes? Okay, and obviously it's a topic of great interest here. For the purposes of today, I'll really focus on the first question, So I'll talk about role of magnetic fields and how we want to get this out of black hole imaging, what we've done so far and what we hope to do. But I'll also add at the end that to me, these areas are related. That the signatures of, say, the infalling gas and how it's shown in polarization signals that I'll talk about. If you want to study the gravity aspects, you really want to be able to disentangle those two things. And so knowing about one is actually maybe very important for learning about the other. Okay, great. So you may have seen this picture on the left by now.
It looked a lot better.
I think I don't really like this version. So only obviously there's a major technical breakthrough in being able to do this experiment. The other point that I want to make is that in my view, it's also a major success of our basic theoretical understanding of how gas falls onto black holes and how it then heats up and radiates synchrotron radiation that we observe. And the basic prediction, especially, again, in my view, from the numerical models that have been developed, is that they generically predict that the radiation comes from very close to the black hole, where relativistic effects will tend to shape it into this ring, where the rotation speeds approach close to the speed of light and give you this asymmetry from the Doppler effect. And that comes out very generically when one tries to calculate what these numerical models of MHD in a fixed curve background predict should be seen in sub-millimeter emission from M87 or the other EHT target, Sag star. And just a nice illustration of this from Monika Mostrowska, just taking one of these models and then just blurring it progressively more, until it sort of looks like the data. Okay, great. And this this type of work done by many groups over many years. And the point is then that I think what's so exciting about seeing this is that then we can hope to push further and do more, because we maybe understand the basic idea, and now let's push forward to really do the astrophysics, in particular my interest of what can we learn about how black holes grow, and push forward. Okay, so the downside of this being a very generic prediction of this type of accretion model is that means that you're also surprisingly insensitive to the details. You might say, just show me the image and I'll know what's going on. We'll know everything about it. That does not turn out to be the case. So this is just a few simple examples, taking very different physical conditions and doing predicted models of the EHT image. The top are high resolution, varying the strength of the magnetic fields in the accretion flow. So do the magnetic fields produce enough pressure to resist infall of gas, or do they not? And varying the black hole spin by large amounts, and also other parameters. And this is not really what the EHT measures, but one illustration is just blur it to a nominal resolution, and they can all look quite similar to the image. Okay, reality is more complicated than that, but the point is just that there's no robust handle here from these images, I would claim, on which physical scenario goes with which of these total intensity images like what's been published so far. Okay, and I would have said there's one very simplifying assumption here, and there's one case where I would have said, well, probably we can rule out this already, or maybe we could for M87, which is if you misalign significantly the angular momentum sense of rotation of infalling gas at large scales from the black hole spin. This has tremendous dynamical consequences for the gas because it's now all the particle orbits are undergoing Lense-Thirring precession, and this naturally leads to crowding of their orbits in two locations around the black hole, which shocks and should produce some bright spots and other features. But two recent calculations shown on a different color scale, but still are not ruled out based on their color scale alone. Two examples showing that actually you can get these asymmetric rings even for significant tilt angles. So even in this case, maybe we can't rule out that scenario just by seeing the ring image. The ring image is extremely robust. That's one reason we're so confident in it. It also makes it very difficult to tell things apart just based on that picture alone.
The tilt angle is between the jet and the spin?
Sorry, no, it's between the angular momentum of the gas at large scales, which is here is prescribed not at large scales, and the black hole spin itself. Yeah, so what it then does is more complicated. The inner parts can start to align or do other things, but Yeah, it's the large scale sort of feeding if you think about the gas source of large scales. Yeah.
In that previous thing, we had the 3 simulation. Yeah, is there any hope of distinguishing between those, by further refinements, extensions of the EHT, or is this?
Yeah, we're gonna do. Well, let's do it. Let's do it in the top. Yeah.
Okay.
Yeah. Great. we have more than just total intensity data. Yeah. There's many ways. I'll give one. Why I'm very excited about polarization in particular. There's many ways that we can do this. Yes. Okay. So one other way to think of the current uncertainties is just asking what is the light source that we're actually seeing in that image. So what are we looking at? Are we looking at stuff that's falling in? Are we looking at stuff that's going out in a jet? And it turns out even this is sort of uncertain. So these are plots in sort of coordinate space around the black hole. The observer is down here, and the light spots are just tracing where the intensity that we see in the image came from. And again, this is 2 examples. One of them where this would sort of be stuff that's flowing in, so this is then the vertical direction and the radial direction. So this would be stuff that's sort of bulk flowing in the accretion flow, I would call it. And then this is something where you're looking from this way, remember. So this would be the sort of towards the wall of a jet, which would be along here, coming at you, and most of the light you're seeing is actually from behind. And so I would call this mostly an image of a counter jet. And it turns out that both of these at the moment remain viable scenarios. So we can't actually tell that again. It's one way to think of the uncertainties that we currently have.
How is it possible that the counter jet is more bright?
Yeah, so I would claim that this is the result of lensing. I know that take is controversial. Yeah. I think in this case it definitely is because of lensing in this model.
So
a lot of the emission, you can see a lot of the emission is from very small radius, and so light bending and lensing will be very significant.
But I want to understand, so the source of the emission is the counter jet or not?
Yeah, it's material that's towards the wall of the jet.
Yes, but it's moving away from us. No.
That probably depends. I think in general this stuff would be moving away from us, but not at fast relativistic speeds. So the main Doppler shift you get is still rotation. This is rotating near the speed of light.
So what's the meaning?
It will maybe start to accelerate away.
So why do you call it a counter jet?
Yeah, okay, you can debate, but it's going to be it's in regions which are going to accelerate into a jet, or at the wall of a region which is going to accelerate fast away.
But what you're seeing is not really moving away.
Exactly. That's why it's the opposite sense of normal astrophysical jets, right? Where you see the part that's coming towards. It's exactly right. Yeah. Okay. Great. All right. So let's get around these.
Why are you calling it a counter jet if it's not moving away?
Because this structure seen at larger scales would be associated with a traditional jet, which is moving away. So it's going to accelerate.
So it's the base of something that may eventually...
Right now it's moving like this at high speed. It's going to keep moving like this, but it's going to accelerate away and become a jet. So it's the base of a jet, if you want. The name is in quotes. It shouldn't be so...
but that's assuming a lot about the dynamics, isn't it?
What's that?
That's assuming a lot of...
We have the dynamics in the model.
But
this is a picture of a model. We have the dynamics.
Okay,
I'm
so
saying these two models cannot be ruled out. In this model, that thing's going to become a counter jet. That's so bad. It doesn't seem so bad. Right. We'll probably do worse than this later. Okay, great. Great. So to me, one of the immediate things we can do, there are many approaches to breaking these mild degeneracies. To me, the most immediate approach is that we can look at polarized intensity. So what we see is synchrotron radiation. Synchrotron radiation has a preferred direction, which is the magnetic field, and so it's very highly linearly polarized. We can look at that with these experiments, and this has been studied in unresolved data for a long time.
And is it part of the quote-unquote disk that's lit up here almost all inflow, or do you have some layers on the outside that are also moving out?
I mean, come on, this stuff is flowing in. I'm pretty
but
sure
you'd have to get to higher
I'm pretty
angle.
confident of that.
Okay.
Yeah. All right, I'll stop. I'm trying to give them these nice names, but then nobody likes the names. It's complicated, right? But okay, that's fine. Okay, and so the point is that if we can make resolved polarization maps, the argument is then we can break these degeneracies by, for example, measuring what is the structure of the magnetic field around the black hole, and what are the plasma properties. So how hot are the electrons, how dense is the fluid, and so on. So we'll go through those, starting with the strength. So the first thing to know is that as we understand rotating accretion flows, the magnetic field direction should also encode its strength. And strength here means, is it dynamically important? Is it being dragged along with the fluid and sheared out, or is it able to resist being dragged around to some amount? Okay, so the point is that if the magnetic field is weak, it will be sheared by the rotating gas, and it will end up in a very toroidal configuration, right, wrapped around the black hole. And remaining vertical or poloidal is only really possible if the magnetic fields are strong. Okay, and we have names for these two limits. You can blame Ramesh for these. They are sane, standard and normal evolution, the weak case, and mad, magnetically arrested, which is the idea that if the magnetic fields become strong enough, they could in principle balance, well they can in the simulations, balance ram pressure of infalling material and make it actually sort of difficult for material to fall onto the black hole.
Is there a third option of very turbulent, kind of not organized?
So this one is supposed to be the most disordered you could get, I guess I would say, because the fields are weak, so they can be flung around by the gas. They're driving magnetic turbulence. So we're supposed to be here capturing how turbulent they should be. They end up being quite ordered because the shear is so strong. So maybe there's a more disorganized limit one could come up with, but I'm not
actually sure.
In both cases
you have organized fields. Yeah.
We'll see that in a minute probably. But yes, I think that's sort of a result though, not something that's put in. I think it could have been the case that turbulent fluctuations were even larger, maybe, and maybe then it wouldn't have been so ordered. I don't know that one's obvious. Yeah, it had to be that way.
It would be nice to see if nature obeys by this assumption.
Yeah, would be great. Okay. And the other thing is that, so basically we're saying if we can measure the direction, the pattern of the magnetic field on the sky, we can say something about how strong magnetic fields are, which we would love to know. This is a basic parameter in estimating how much energy can be extracted in jets, for example, how the black hole is actually growing, and so on. So we would love to do this. And the argument is that we can do this. That when we measure the resolved polarized image, which I will draw on top of the colors, their total intensity, the ticks are polarization. In this case, their length is proportional to their strength, and their direction is the electric vector position angle, so the electric field of the polarized photon. Okay, so we have now two limits, and we claim we can tell these apart in principle. So on the left is our toroidal case, so weak magnetic fields gives a pattern like this very radial type pattern. And if it's, in this case, vertical, but if you do general poloidal cases, they look fairly similar to this, and you'll get these sort of twisty patterns which are related to strong magnetic fields.
These are electric vector ticks, so
right.
The magnetic fields are...
You could do that, but I really wouldn't advise doing that here because this is purely vertical. So that's not going to look purely vertical if you do that 90-degree. Anyways, whatever. The B of the photon is not going to be the B of the gas.
How would the go ahead.
Yeah.
Do you, two questions in one. Do you map these as electrons or protons? And is there any observation which defines that they must be photons or electrons?
So the radiation is from electrons. It's synchrotron radiation from electrons, is the assumption.
That's the assumption. And it's not known if that's true.
Well, that should be the case. So they should, we think the fluid that's infalling should be protons and electrons, and the proton radiation is suppressed by
I think that assumption will be guided by what the magnetic field structure is, and so you must have a much more complicated picture there. In other words, the magnetic field could be poloidal with the accretion disk, or it could be north to south, or like an electromagnet. And then within that, you've got the uncertainty whether you're dealing with the electrons or the protons.
So the electrons are what will produce the radiation that we see.
Well, of course they will. We know it's observed as synchrotron, but the protons are there, I presume.
They're there. Yeah, we have protons.
Do we see recombination then?
No, the temperatures here are enormous. These are actually relativistic electrons. A typical temperature would be like 10 to the 10 or 10 to the 11 Kelvin, which is extremely ionized.
Thank you.
Yeah, relativistic electrons. Okay, great. So very quickly, I just want to explain how these come about. So the polarization pattern that we see ends up perpendicular to both the line of sight direction and the magnetic field and synchrotron radiation. So if we do toroidal fields everywhere, B in these diagrams is in blue. And so the line of sight, say we're looking just straight down, then you can just do that the polarization pattern should go like this. So toroidal magnetic field leads to a radial pattern in our polarization in the end. Okay. So the other case that we were talking about of purely vertical is a little more complicated because if you're looking straight down again, and you were saying that the magnetic field is pointing straight vertically, meaning out of the screen, then you would get 0. But that's not quite the case around the black hole. So even if this is highly idealized, is not what we really expect in nature, but even in this simple case of extremely vertical field, you would still get a polarization pattern that's non-zero, and it's because you have light bending towards the black hole. So you have a component, effectively, one way to think of it would be that you have a component of your wave vector which is pointing in towards the black hole, sort of schematically drawn in yellow there, and this will give you a magnetic field pattern which, the combination basically of, if you're at some inclination, the polarization will always want to be horizontal. If you're directly looking straight down, it will have this twistiness. The combination of those in general gives you something that looks like this. Great. And I just want to point out, so these are just example simulations. These are very simple maps with these fields just prescribed by hand, but the same limits turn up in simulations that we do. So these are just images showing these limits. This thing, it's 3D, it's turbulent, so it's not quite perfectly a radial pattern, but mostly like that. And this one is one of these MAD simulations, so it's relatively strong magnetic fields, and the pattern ends up rather twisty here. Okay, and so the hope then is that with polarized imaging, the pattern of the polarization on the sky can tell you about magnetic field strength, which would then break a lot of these degeneracies that we see.
Might also depend on frequency, right?
Yeah. So in particular, I think I took it out really short on time. But these effects, this is all 230 gigahertz. If you go to 345, the other complicating effect I'll return to later, Faraday rotation, essentially goes away, or should in large part go away, and then it's even more imprinting the meaningful. Okay, but the other thing that you can do, so this will come hopefully soon with the Event Horizon Telescope data, but the other thing you can do is you can go to the near infrared, where we have these measurements now, not of a resolved map like this, but also explain, I think we have information actually about magnetic fields in the galactic center from near infrared data now. Okay, so the main thing we see in the galactic center, this is in the galactic center now, not M87, with Sagittarius stars, that there are very bright flares in the near infrared. So it's highly time variable transient emission where the brightness changes by factors of 10 or even 100. Sorry, 10 does not actually equal 100. That I believe is a typo.
Over which time?
Okay, on sort of timescales of half an hour to an hour or something like that. This is a really bright flare, the brightest ever seen reported by UCLA earlier in the summer. Okay, and this brightness, so the source here is unresolved. It just appears as a point source. But we can actually, with gravity, we can spatially resolve it. We cannot image it, the resolution is not good enough, but we can basically look, accompanying with these brightness changes, what is the center of light doing in position on the sky as a function of time. And this was done last summer for 3 different of these flares. And the conclusion is that we consistently see clockwise rotation of the center of light of the source at a scale that's something like 3 to 5 times the Schwarzschild radius expected for the black hole in the center of the galaxy. So here's one example where these points are color-coded by time, going from red to green to blue, and you see this rotation in this direction, where the black hole, it looks like we're orbiting around this point in purple, and the black hole position expected is marked by the orange cross and arrows. Okay, we basically interpret this that the scale is 3 to 5 Schwarzschild radii, the rotational velocity is something like 20 to 30% of the speed of light, and those are roughly consistent with what you might get from an orbiting compact emission region going around the black hole. Okay. Great. And if you put those together and claim it's in orbit, then the other way to say it is that you would have an answer for the mass enclosed, which is consistent with what we think we have for the galactic center. Yeah.
Just repeat again, what is the pink cross and the yellow?
Yeah, so the pink cross is kind of what we think the median of the data points that it looks like we might be orbiting around. And the orange is if you just take what we know about the orbit of so this is all reference to the star S2, the star that we showed orbiting the galactic center. So if you take what we know about that orbit and say, where do we expect the black hole to be based on what that star is orbiting around, with some error bar, that's this.
So one sigma.
They should be on top of each other.
Yeah, ideally they would be exactly on
just
top.
one sigma.
Sort of shocked
it's
that
okay.
it ends up that close.
Okay.
That's it.
And
We're not recording this, are we?
well,
Supposed to be on.
and you've taken the centroid and traced it,
Yeah,
but
that's right.
the emitting region could be
Yeah.
fairly widely distributed.
Right, so the argument generally is that if you have really large amplitude, rapid variable emission region, then probably it's not too big. So that's one argument. It could be more complicated, but it's not that big. And here, if you see it continuously moving, I think the main question is whether that's a pattern speed or a real dynamical motion. But something seems to be continuously moving. It's not over here,
Over how
and
many
way over
orbits?
here, and then way over here. This is the duration that we've seen. It's
So-
hard to do for long periods of time. We do it really well when the source is really bright, and that lasts for about half an hour or 40 minutes. It's
So
hard.
that's 40 minutes, so
This whole thing is 30 minutes, sorry.
I'll let you go. But I was gonna say there must be some limit on density, temperature, magnetic field if you were gonna assume that it's a small region that remains coherent, it doesn't shear.
Yeah, that's right. So we've actually done this. So Miki Babak is a postdoc at MP and done a lot of this modeling and has looked into this. Can you place some constraint on size based on shearing? And we don't see it long enough. So if you saw 3 orbits, that would become quite constraining. But we just don't see it long enough to place really good limits. Okay. All right. So the interpretation, colorfully illustrated, goes back to a proposed mechanism for flares by Avery Broderick and Avi. That maybe you just have some compact blob called a hotspot that is actually orbiting around. So this red part would be our flare around the black hole. Okay. So the point for the magnetic field part is that the polarization map, we aren't actually resolving a polarization map like we wanted to do to measure these types of patterns, but we are now getting this information maybe by sampling different regions around the black hole in time. So if we have this type of a blob, which is then orbiting around, it will light up different parts of the region around the black hole at different times. And so if you had a background magnetic field, you'd be sampling it differently in time, and from the time signal, you could reconstruct what it looked like in space. Okay, so let's try to do that. So we had one flare where we actually measured the polarization well. You can ask me about that later. So shown in blue is the total brightness in some units. This was a double peaked flare here. And this in orange is the polarization angle, which is steadily changing. So this is related to the orientation of our ticks. So it's basically saying we've gone around our ticks from vertical to horizontal and back in what is about one period of what we infer to be one period of this motion around the black hole. Okay, and I won't go through it again, you can ask me about it, but basically because of this radial pattern switching on and off, if this were a weak toroidal field example like we showed, we would have expected this to move twice as fast as the orbit itself. That's not what we see. We see it to be about 1. And it turns out the easiest way to explain that is with something like this vertical field example that I showed. Okay, so we argue from this that the most likely explanation in this scenario is that we actually see strong magnetic fields near the black hole in the center of the galaxy.
And it's coming strong.
This is a twiddle argument. I would say it's got a significant vertical component which leads to a twisty type map.
Yeah, but how?
We're actually,
what's the in Gauss?
Tens of Gauss.
Yeah, those are fine. Yeah,
10 to 100.
but the weak field can
No,
also
because
be tens of Gauss.
If you know the magnetic field strength, you might then figure out something about the emission.
Yeah.
The electron distribution.
That's right. Yeah, I think it's not. So strong versus weak here is not such a large factor that it would make a huge difference in B. So I'd say B is probably like 100 would be my guess, 50 to 100.
And that's equipartition.
It's a little bit weaker. Yeah, a little bit weaker than equipartition. Comparable to equipartition. Okay, great. Right,
So you're saying we're seeing a face on orbit and the magnetic field is coming at us?
No, the verticals.
So I think the constraints on inclination are not that great. The main constraint on inclination is that we don't see evidence for very strong Doppler beaming of this emission region, which is supposed to be at 3 to 5 Schwarzschild radii. So the total flux changes do not correlate really well with position. And so that argument is that maybe the inclination is less than something like 40 degrees. But it's not a very, I wouldn't call that a super strong constraint. It does not need to be phase-on. Okay.
Sorry, I'm just confused.
Yeah.
This is the gravity collaboration 2018. So this is data?
These are data. This is real. This really happened.
And this is infrared data, so the polarization is not dependent on Faraday.
Yeah, there's no Faraday rotation, which I'm about to skip in the interest of time. Yeah, that's right. So this really should be seeing magnetic field. The problem, the issue here is that we have a scenario that we're saying, but what if something else is driving the polarization? So we think it's compelling that a very simple picture explains both the astrometry that we see and the polarization, but we have to make that assumption in order to get at the magnetic fields here. Yeah, but we can do it. It's great. Okay, so as I said, I'm going to skip there's another important effect where we can measure properties of the plasma using how scrambled the polarization is, and that could help us decide where it's coming from. So just as one example that I want to try to explain, if you look at different scenarios for M87 now in EHT data, one of them where the emission is coming from what I've called the counterjet, so from behind the black hole, it might be very scrambled. The polarization map that we see might be very scrambled by interactions with the plasma, dense cold plasma that we don't otherwise see, but that the polarization is sensitive to. Whereas in the case of where the emission is instead coming from in front, and you don't go through this dense cold region of electrons, you might see something very, very ordered. So it's not only the pattern that we see, but also how scrambled it is that can give us really valuable information, for example, on where the emission is coming from. Okay, and the very last thing that I want to say is how this might be of use if you want to get at general relativistic tests. And the main feature that we expect to be there in signals from near black holes is that light can go around in a circle, and the size and shape of that feature projected on the sky, what we call the photon ring, is a prediction of, say, the Kerr metrics. It's something that we could use to get at relativity. And the argument here is that basically it's 10% or so of the total flux in most of our theoretical models. So to get at it with precision, we need to be able to separate it from direct emission, which is just coming towards us from the gas on similar scales. And one way that I think is promising, or might be promising, is to look at the polarized flux. So here's an example where we have a total intensity, one of these ring images, and now we look at the total polarized intensity. And you might say it looks pretty similar, except that there are these sort of darkened patches. And it turns out that the locations corresponding to this photon ring tend to be quite depolarized compared to everything else. So if you're able to subtract the two, the residual ends up looking like a bright ring. The caveat here is I don't know how to do this. So if anyone has any ideas, please get in touch.
Why don't you know?
Because this is square root of q squared plus u squared,
Okay.
and square roots and squares are not great in Fourier transforms. Convolutions, you need full UV, it's not great.
And you can't do it in the UV plane.
I would love to.
But
Yeah.
doesn't
Give an
very long
idea.
baseline exactly get to this higher resolution to this?
Say it again. Sorry.
Doesn't the very long baseline exactly pick out these higher frequency components on the right-hand side?
Yeah, you mean if you could make this. I think the question is with current resolution, current type of data, or near future data, could you just make this picture in the UV plane and then image it, or just measure stuff from it? That's what I don't know how to do. Okay,
Do
but I'll
you
just.
expect this ring would be changed if you consider a square of both of them? Because
So
if you consider I square and then get rid of a square root, then you just
Right. I think the challenge. So I think the basic challenge is that you can't enforce positivity of a polarized flux in the UV domain, for example. I think it's a more fundamental issue than an operational one, but I would be delighted to talk about it more. I think it would be great if we could do it. Yeah.
Do you understand why it's not polarized? It just
Yeah,
comes out of the simulation.
I'm really trying to look at this more because it's not totally obvious. So the two, I guess three sort of ideas. One is that it's the self-absorption of the synchrotron radiation, because these rays are passing through more material, so they have a higher optical depth than everything else. So if the other stuff is at, low but not zero optical depth, maybe this stuff gets self-absorbed and that will depolarize.
And that depends on frequency, so you can check if that's the correct interpretation.
That's a really good idea. Yeah, okay, thank you, I will. And the other idea is maybe that it has to do with either Faraday rotation, just again passing through more stuff, having more chance to get rotated around randomly, and or the parallel transport, which does something kind of similar. But I don't have a firm answer. I guess I'm sort of leaning towards optical depth, but I'm not sure. I will test it, yeah. Okay, great. So just very last thing I promise. So just to show this in movie form, so you can look at, this is again our total intensity, polarized flux residuals. I just want to say that, again, if you could do this with real data, it works really well if you can integrate for a long time. So the galactic center, where things are changing rapidly, would be a strength if one could do this, because you're sort of thinking of you're using this to kind of clean away all the other stuff, and as it moves around, you're able to do a better job of cleaning. So look at, this is the averaged residuals integrated over time for one example, where you can kind of see that as time goes on, as you do the subtraction better and better, maybe this one's even better, and you can see how it actually gets better as time goes on.
Is this flickering like real, or is it the scale of the movie that's flickering?
Wow, that's a great. Okay. Sorry, flickering.
You see like the background lighting up and.
That's probably a color scaling intensity.
Okay, so that's
right.
not.
Yeah, that's right. Yeah, so it depends. You have to do the subtraction in some suitable way that you figure out, because the normalizations are not different are generally different of the total and polarized flux. This is not finely tuned to get the best answer. Yeah, I'm finishing. Okay, great. So summary is that resolved polarized maps that we can now or very soon make will encode key signatures and break key degeneracies in understanding what we're seeing in images like the HT image. And I think it may also be useful for getting at this photon ring signature of GR. Thanks a lot.
Questions to Jason?
So the electron vector polarization angles were obviously more ordered versus more scrambled, depending on whether you have initial field that's toroidal versus vertical. But if you don't have such starkly diametrically opposed cases, could there be another way to actually measure the differences in the disorder? Like maybe instead of using EVPAs, using Stokes Q, Stokes U, Stokes V, and seeing what symmetries and asymmetries you have, and measuring degree of symmetry by, I don't know, image moments or something like that.
Yeah, it's a great question. So the best way that I'm currently aware of to measure this stuff is work by Daniel Palumbo, who's back there, in trying to measure essentially what is the rotationally symmetric pattern of the polarization look like, and quantifying that. I think the first key result of this stuff is that these simple limits we showed that look quite different map onto physical scenarios that we might expect. There's probably stuff in between there, but it's a pretty narrow, finely tuned range in parameter space to get in between. Probably the fields are either weak or they're strong, would be my guess. But there may be things in between, and I think we can quantify that.
So Jason, last week we had a colloquium by Oliver Pott.
Okay.
And he showed us simulations of mad GRMHD simulations. And he had this nice idea triggered by the movies that when you have a mad accretion flow, the gas comes in these clumps. And every time there is this interchange, a bundle of field lines which are pushed against the black hole spring out.
Yeah.
Then they orbit around and then they get pushed in again. So if gravity is really seeing these bundles, if the flare is a bundle which first springs out and then orbits, you might be able to see that.
Yeah. So let me just show.
Yeah.
In the idea stage.
Yeah.
But we see this. So these are. Sorry, this is not really for presentation so much, but anyways, this is electron temperature in the midplane in a large scale after one of these events in this MAD simulation, like Ramesh was describing, and we see features which are at interestingly large scales, which go around.
Question is, are
and
they bright?
Have interesting features in infrared
but are they bright when they are going out? And could you see that in gravity?
I see.
starting from the center,
Right.
going out quickly radially, and then
Right.
going around.
Where
Yeah.
they may lose their brightness.
I think it's
Or
very.
they may not get bright enough
Yeah,
until they reach.
exactly.
But the question is,
Yeah.
we can look in the data and also probably look in the simulation.
Yeah, I think there's a lot to. So I don't know what
Yeah.
Oliver showed, but I'd say for me, theoretically, there's a lot to understand. For instance, in this picture, I don't actually know what sets the time scale to go around.
Oh, he had the things going to different radii.
Okay.
So sometimes it goes to radius 6,
All
sometimes
right.
it goes up to 20,
Okay.
So I guess wherever it stops will
Then
set,
it orbits.
will set your
Okay.
period. Yeah.
That's very interesting to look into.
Yeah.
We're looking into it too.
Mhm.
Okay, let's thank the speaker again. Jason is around for the rest of the day, so he'll be happy to talk with you some more.